All right, 8.2 homework. Let's look at number one. Let X be a random variable that represents the pH of um, arterioplasma. For healthy adults, the mean of the distribution is 7.4. New drug for arthritis has been developed. However, it's thought the drug may change the blood pH. So, random sample 31 patients who took arthritis took the drug for 3 months. Blood tests showed that the sample means 8.6 with a mean sample standard deviation of 3.1. Use a 5% level of significance to test the claim the drug has changed either way from the mean pH level of the blood. What is the level of significance? Now, they said it was a 5% level of significance, so you need to express that as a number. So we're going to do it as a decimal, so 0.05 there. So 5%, 0.05. Let's look at the hypothesis here. The Ho is always equal. And here I'm testing the claim that's changed in either way. So change in either way would be a reference to the what, or reference to what? Less, greater than, less than, or not equal to? Not equal to. So change either way would be different. So not equal to. So Ho is always equal there. This just changes by whatever you're testing. What distribution will I use? Well, the question is, do I know the population standard deviation? Do I know sigma? No, I do not. I know S, the sample standard deviation. So when I know sigma, I use the standard normal, but when I don't know sigma, when I know S, I'm going to use the student's T. I use the student's T because the sigma is unknown. You could do the t-test in SALT. So SALT will do this for you. So I'll click use SALT. Okay, it's kind of similar to the last unit we did. It's just the same menu. Inferential statistics, one sample T, because it's one sample and it's a T distribution. The sample mean, let's go back up here and figure that out. The sample mean is 8.6. The sample standard deviation is 3.1. So 3.1 there, and then a sample of 31 patients. So 31 goes here. So sample mean, I'm sorry, I moved this. 8.6 is your sample mean. Sample standard deviation, 3.1. Sample size, 31. This is a hypothesis test. The hypothesized mean, that is your Ho, which is, in this case, mu is equal to 7.4. So 7.4. And what am I testing? I'm testing not equal to. Not equal to. So it's a two-tailed test. No, not equal to. Scroll down here. Move this out of the way. Generate results. So you'll have your test statistic and your p-value. Okay, you'll like these. It's not too bad. Test statistic, 3 decimal places, so 2.155. And then you're going to classify your p-value in an interval. So 0.039, 0.039, that should be right in there. 0.039 is between 0.020 and 0.050. Okay. What does the distribution look like? Well, it's not equal to, so that means it's a two-tailed test. It's going to have two, you're going to look for two tails that are shaded. So just like that. So two tails that are shaded. Okay. Now, the question is, let's compare our p-value to alpha. Our p-value is 0.039, our alpha is 0.05. Is 0.039 less than 0.05 or greater than 0.05? It's less than, right? When p is low, reject the Ho. So when p is low, since this is lower than that, we reject the Ho. And when you reject the Ho, you're concluding it's statistically significant. It's like saying someone's guilty. It's like basically in a trial, if you reject Ho, you assume they're innocent, you prove they're guilty. You've proven they're guilty. So that means that you have significant, sufficient evidence to prove. So what that means is if it's significant, that means there's sufficient evidence to prove that the drug has changed. So we were able to prove there using the test that that gap is significant and therefore the drug is changed. So there you go. All right. Number 2. A random sample of 41 adult coyotes are in region of northern Minnesota with an average age of 2.07 years with a sample standard deviation of 0.84 years. However, it's thought that the overall population mean age is 1.75. Does the sample data indicate the coyotes in the region tend to live longer than the average of 1.75 years? Use alpha 0.01. What's your level of significance? That's alpha. So 0.01. It's just alpha. State your null and alternate hypothesis. Well, it's always equal, and it's equal to the claim, so 1.75. And what am I trying to prove? I'm trying to prove they live longer. So if they live longer, is that greater than, less than, or equal, or not equal to? Greater than. So I'm trying to prove they live longer, so it'd be greater than 1.75. Which distribution do I use? Well, it comes down, do I know the population standard deviation? Do I know sigma? No, I do not. I know S. I know the sample standard deviation. So when I don't know sigma, when sigma is unknown, I use the student's t. When sigma is known, I use the standard normal. Okay. What's the value of the test statistics? You can click use SALT. I can use my SALT window I already have open. I'll change this here. 2.07. 0.84, sample size 41. And then my hypothesized mean is this, 1.75. And I'm trying to prove greater than, so my alternate's greater than. Okay. So real quickly, my sample means 2.07. That's my X bar. Sample standard deviation is 0.84. Sample size 41. And then my hypothesized means 1.75, and then it's greater than, because I'm trying to prove it's greater than. And then from this point, I can generate results. Move this out of the way. And so it will generate results for me. There's my test statistic. There's my p-value. So I'm going to use those. Test statistic, 3 decimal places, so 2.439. So that's my test statistic. My p-value, 0.0096. That is less than 0.01. Okay, barely. Okay, less than 0.01. Now, on this one, it's a greater than, so it's going to be a one-tail right tail. So one-tail right tail. So I'm looking at a right tail test. So I'm looking at that. Greater than, so it'll be right tail, upper tail. Now, let's compare this to 0.01. Is my p-value less than 0.01? Yes. When p is low, reject the hoe. So when p is low, we reject the hoe. It's like saying someone's guilty. So we reject the hoe and conclude it's statistically significant. So basically, this average age of coyotes in that region looks to be significantly larger than the average. So they're living significantly larger or longer lives there than they would on average. So let's interpret the conclusion. So if it's significant, you say there is sufficient evidence. Like proving someone guilty, you have sufficient evidence to say that the coyotes in this region tend to live longer than 1.75 years. Okay. So you might get different, some people might get different answers. It looks like most of y'all get similar answers there. Okay. Let's look at 3. Weatherwise, the magazine published by the American Meteorological Society. One issue gave a rating system used to classify weather storms that frequently hit New England, caused much damage near the ocean. Severe storms average peak of a height of 16.4 feet before hitting the shore. Spurs and nor'easters in progress severe at the severe storm rating. peak waves are usually measured from the land from off fixed cement piers. Suppose that a reading of 32 waves showed the average wave, sample mean 16.9. Previous studies showed that the population standard deviation, the sigma, is 3.5. Does this indicate the storm is temporarily increasing above the severe rating? So the severe rating is here. What's our level of significance? That's our alpha, so that's 0.01. I was getting ahead there. What I was saying was our rating is here, so our HO will be equal to 16.4. I'm trying to prove that it is increasing, so I will be trying to show what here? Greater than. So I'm trying to prove it's greater than. What distribution will we use here? Well, the question is, do we know the population standard deviation? Do we know sigma? Yes. So if sigma is known, we use the standard normal. Now, the standard normal, if you want to do it by technology, you got to use your calculator. This is a z-test, standard normal z-test. Your SALT will not do this for you. So stat, test, z-test. Stats, mu naught is my hypothesized mean. Sigma is my population standard deviation. X bar is my sample mean, 16.9. N is my sample size, 32. And I'm trying to prove greater than. Whoops, I didn't mean to do that. Greater than. Okay. All right. Ready to calculate. I could have also picked draw too. I like the draw feature better. Z-test. Do the draw feature so you could see the curve. It's gonna have some shading on the right side of it because it's a right tilt test. So my test statistic is how many? 2 decimal places, so 0.81. My p-value is 0.2095. So that's between 0.1 and 0.250. Sketch the curve, so it's going to look like this one. It's a right tilt test. And then is our p, let's evaluate our p-value and compare it to the alpha. Is my p-value less than alpha? No. When p is low, reject the HO. But p is not low here, so we fail to reject HO. And when you fail to reject HO, it's not significant. So basically, this is not guilty. So not significant and insufficient evidence. So we don't have evidence to say that the storm is increasing above the severe rating. So yeah, there's a gap in the average, but it's not a significant enough gap. All right, let's look at 4. All right, this weather-wise thing again. You got the similar context here. Previous studies, okay. Sigma is 3.7. Okay, so similar setup from the last time. A couple things to note. One, the population standard deviation is given. We got sample mean here. So null and alternate hypothesis. The HO, so we're going to go back to the claim. That's mu. It'd be Greek mu, and it's equal to 16.4. And we're trying to prove increasing, so it's going to be greater than. So I'm going to actually copy this. Control C, Control V, greater than. Okay. Now, how do I do the test statistic? This is a standard normal, so you're going to do a z-test. Okay. And I've got 16.4. My population standard deviation is 3.7. My sample mean is 17.4. My N is 30. And then I'm going to do a greater than. Okay, greater than. I'm going to do draw this time. Greater than. So my test statistic will be 1.48. Now we have to state the critical region. Okay, so this goes back to the notes. So I'll explain how this works. So the critical region, the alpha, it's a, first off, I'm going to evaluate and see it is a greater than, so it's a right-tailed test. So it's going to be shading out here, zeros in the center. And I need to know the z at that high end. I need to know the z at the high end. Okay, so how do I do that? I can do inverse norm. Now, real quickly, what is this shaded area? It's equal to the shaded area combined. All of it has to equal alpha. So this shaded area is 0.01. I can do 0.01, 0.01, and right. And this will give me the critical z. Second bars, inverse norm, 0.01. And so we'll all have the same answer here. 2.326. How many decimal places do we want? 2 decimal places. 2.33. So what I'm doing here, I went a little too fast there. It has to be greater than, we need for this to be significant, it has to be greater than 2.33. Now, what do I put for less than or equal to? Well, in less than or equal to, there's no bottom boundary. There's no bottom tail. So this will just be none. And so the question is, does my z value of 1.48, does it dip into 2.33? Is it bigger than 2.33? It is not. So 1.48 does not dip into the critical region. So we are going to fail to reject and saying insufficient evidence. Okay. Now let's look at the p-value method. The p-value is 0.0694. That p-value and the alpha is 0.01. How does the p-value compare to alpha? The p-value is greater than alpha. So when it's greater than alpha, here we're going to have the same conclusion. Okay, so you should, if you have them all linked up correctly, you're going to make the same conclusion. So it's going to be fail to reject here, insufficient evidence.